Hey everybody, it's Mrs. Harbin. We're at video notes 10.1. So here's what we're going to be able to do. Here are the main objectives for this unit, for this video. Alright, please read chapters 10 and 17 to get more info. Alright, kinetics. In chemistry, kinetics is the study of how fast a reaction can occur. Alright. There are explosions, food cooks, buildings erode, squirrels decompose. All of that happens, and how fast it happens is what kinetics is studying. Okay? So, when we talk about how fast a reaction happens, we talk about the rate of a reaction. But you can't just talk about rate. You can't just talk time. You have to talk what happens over time. So we do rate is calculated as the change in concentration over a change in time. Okay? So that means that a unit for rate could be molar per minute or molar per second. So what do we take the change in? The concentration of reactants or the concentration of products over time. So that's how we're going to measure rate. But how does rate compare to time? Well, the faster the rate means the less time it takes. Less time. All right? The slower the rate means more time. Okay, so look, they're inverse of each other. Time and rate are inverse of each other. And then to measure rate, we do the change in concentration over time. Oh, look, some data. Okay, so starting at 0 seconds to 300 seconds, the amount of this substance was measured. Okay, what was it measured in? Concentration. So the concentration was measured at these time intervals. So what's the rate? Well, if we want the rate here, we do the change in the concentration divided by the change in time. Okay, so look, it's negative. Why is it negative? Because the amount of this material decreases. So it's a change of -1 times 10 to the -4 moles per liter, molar per second. Okay, so is rate constant? Well, you can see you could do a rate, overall rate, but this changes by 0.006, this changes by 0.006, and this changes by 0.005. And then this changes by 0.003. So rate is not constant for a chemical reaction, but we can figure out the rate at different time intervals and an overall rate for a chemical reaction. All right? So what do we mean rate of a chemical reaction? Well, reactions occur in steps like baking a cake. If you want to bake a cake, you have to mix the stuff together, you have to pour it in the pan, and you have to bake it. Okay, so so in a chemical reaction, the rate determining step is the slowest step, and it controls the rate. So out of these three steps, what do you think the step that controls the rate is? I would think this one, because it probably takes about 40 minutes to bake the cake. So the rate determining step of cake baking is step 3, baking. All right? And so what a chemist would try to do is find out which one's the rate determining step and maybe try to add a catalyst to change that step, because changing that step would change the overall rate. Okay, so what determines the rate is the slowest step in a reaction. What do I mean by slowest step? Well, if you see a reaction that is A turns into F, and that's one step, then that's called an elementary step. Okay, so if this is your chemical reaction and this is exactly what happens, then this chemical reaction goes by one elementary step. But look at this chemical reaction. All right, this happens in these 3 steps. So first A and B turn into C and D, then D and E turn into F, then F and C turn into G. So what we do with the elementary steps of a reaction is we add them together. So A plus B plus D plus E plus F plus C. Why do I do all that added together? Because they're all on the left side of the arrow. C plus D plus F plus G is all on the right side of the arrow. But then I look to see what cancels out. F cancels out, D cancels out, C cancels out, so we're left with A plus B plus B plus E equals G, or produces substance G. So what do we call these other things along the way? Those are called intermediates. All right? Intermediates are not reactants and they're not products, but there's something that forms along the way. Okay? So a chemical reaction maybe occurs in steps. Those steps are called elementary steps, and then adding all of those steps together gives us our overall chemical reaction. Things that are made in one step but used in another are called intermediates. So why do chemical reactions even happen? Or how do they even happen? Well, first of all, particles have to collide to react. They have to hit each other to react. Not just any collision, but a collision with enough energy. Okay, what do we call that energy? It's called sufficient energy, and that sufficient energy is also called energy of activation. Okay, activation energy. Enough energy to get the reaction going is the sufficient energy it takes. Okay, and not only that, they have to hit each other at the right angle. Okay, that's called orientation, the angle of impact or the orientation of the molecules. So these three things together cause a chemical reaction to be successful. Okay, that happens in all chemical reactions. So what influences the rate of reaction? Well, these 6 things can be talked about to influence the rate of a reaction. So we already know that a reaction is caused by collisions that are effective. In order to be effective, they have the right energy in the right angle. So how does the mechanism influence the rate? Well, each step takes time, and the slowest one determines the rate. How does nature of reactants influence the rate? Well, nature of the reactants, things we can't control. This reactant would be very complex. Okay, these reactants might be a little less complex. So the nature of the reactants has a lot to do with how complex the molecules are and whether the reaction will be fast or slow. Okay, so what does orientation mean about collisions? Well, so this reaction happens. How can it happen? 2 of these have to collide with the right energy at the correct orientation. So if they collide like this way, then the bromine breaks off and the NOs break off. So that's a correct orientation. If they collide this way, the bromine breaks off and the NOs break off. So that is the right orientation. If they collide this way, then this molecule and this molecule will be exactly the same when they're done. So that's not the correct orientation. Okay, so molecules have to collide with the right energy at the right angles, correct angles. What else can influence reaction rate? Temperature. Okay, well, when we talk about temperature, we're talking about increasing the motion, the average kinetic energy of the molecules. So higher temperature is going to mean higher energy and more collisions. More collisions. What does that mean? Faster rate. Okay, so what is lower temperature? Is going to mean lower energy, it's going to mean less collisions. So it's going to be a lower rate. So this is higher rate, this is lower rate. Okay. Concentration. Why does concentration affect rate? Well, concentration means how many particles are in a certain area, molarity. Okay, if you have a high molarity, there's going to be more collisions. More collisions means more reactions. Okay, lower molarity means less collisions. Less collisions means less reactions. So this is higher rate, this is lower rate. Surface area. So there we have our chunk of sugar. And here we have the same amount of sugar, but lots of tiny pieces. This is increased surface area, means more collisions. Okay. More collisions means more chances to react, so it means higher rate. Okay. This is less surface area, less surfaces to contact, because this you can hit all around, this you can only hit the outside. So that's less collisions, because less molecules are exposed, so lower rate. Alright, catalysts and inhibitors change the rate of a reaction, and we'll talk about that later, but this is keep posted. Alright, so one thing that we use to help us describe chemical reactions is the heat. Heat is enthalpy, delta H is heat. Heat is enthalpy, delta H is heat. So just remember, positive side of positive H, left side of the equation is endothermic. Feels cold is endothermic. Okay, on the left side of the arrow. Boiling water is endothermic because the energy goes in, the water molecules absorb energy and leave, so that's endothermic. Added in endo. Okay, so energy diagrams. Well, we have 2 kinds. We can do an exothermic energy diagram. We can do an endothermic energy diagram. Okay, which would start like that. Okay, so always we have reactants and products. Reactants and products. Okay, activation energy. All right, so this is why I was playing Miley at the beginning. Activation energy is that sufficient amount. It's the climb. Get it? It's the climb. Yay. Okay. So it's the energy that those particles have to collide with in order to activate the reaction. The substance we have at the top of the hill could be a transition state or an activated complex. 2 words we use for pretty much the same thing. All right. So when do you have that? Well, that's the most unstable part. It's the top of the hill. Okay, how do you get there? Activation energy, and then products are what you get when you come down the energy hill, And the difference between reactants and products is delta H. All right, this delta H is negative. Products minus reactants gives you a negative number. This one, products minus reactants, is a positive delta H for endothermic. Make sure you can do that for every energy diagram. Okay, fast or slow. So this is where catalyst comes in. So if you have an energy diagram, and then you have another energy diagram, all right, so this is a slow reaction because you got to climb this energy barrier. This is a faster reaction because it has a lower energy barrier. So which one's going to be faster? This one. Okay, these are both exothermic. Well, what does a catalyst do? So a catalyst might give this reaction that was slower to start with a new pathway so that it only needs this much activation energy. So instead of using the old mechanism that had this much energy required, it only needs that much. Okay, so a catalyst increases the rate by lowering the activation energy. An inhibitor messes with the catalyst so it can't do its job as well. All right, energy diagrams in terms of bonds. So again, energy diagrams. We're doing a lot of them. Exo, endo. All right, so why do we always have to go uphill first? We have to break the bonds. So breaking bonds absorbs energy. Every chemical reaction will go uphill first. Oh, look, it's an endothermic reaction. But guess what? It goes uphill first to break the bonds. Then, after the activated complex forms, energy is always released when new bonds form. Okay, so energy is absorbed to break bonds, released when making bonds, forming bonds. Breaking absorbs, energy is released when new bonds form. Okay, always. So, what's the difference? Well, it looks like these products released more energy when they formed than it took to break the original. Okay, so bonds breaking absorb energy. That's your BA uphill. Energy is released when new bonds form. When new bonds form, so that's the RF. Every chemical reaction has to barf. Okay, if the energy that's being released when forming is more than the energy it took to break, then it's exothermic. If energy breaking the bonds is more than the energy released, then it's endothermic. Okay, so how are we going to be able to calculate this enthalpy we've been talking about? Well, there's something called Hess's law. Hess's law is considered a state function. That means enthalpy, is considered a state function. So that means it doesn't matter how you get there as long as your start and finish, you know. Okay, so here's a chemical reaction. Here's the start, here's the finish. Doesn't matter how we get there. So we can use this chemical reaction, and add them together using our arrows as an equal sign. So we have Mg plus half O2 plus CuO, all on this side, right? Gives us MgO plus Cu plus half O2. Right? So we can add these together, but then look what's happened. The oxygen cancel out because it's on both sides. Right? And then we have Mg plus CuO gives you MgO plus Cu. That's this reaction. So we can add these two reactions together to get this reaction. Each of these has a delta H, so all we have to do is add those together. Okay, so negative 604 plus positive 155, and we get negative 449 for the heat of this reaction, even though it doesn't matter how you get there, as long as you get there. It's a state function, so we could add those. Okay, what about this one? If we want to make this stuff, hey, these two reactions have delta H's that could be given to us. So there's a series of reactions. If we add these together, we get 2 carbons turning into, oh, wait for it. Oh, that's what we got to do. 2 carbons turning into, let's see, we got an oxygen here. Here, I'll just erase and start over so you can see. So we bring down all of our reactants, 2C plus 2O2 plus 2CO2. Arrow, 2CO2 plus 2CO plus O2. All right, yes, they all have states, but we're looking. So carbon dioxide cancels. All right. This is 1 oxygen on this side, put 2 on that side. So this one is canceled by the 1. And so now we have, this reaction, what we have left is this. So these two add up to this. So then all we have to do with the delta H's is add them. And we get negative 221 kilojoules. Okay. So does it get more complicated? Yeah. Check this one out. This is so fun. Okay. So we want this overall reaction, but we only have these 3 series of reactions to use. All right. So I'm going to look at these and add them up. Well, this is NO, this is O3, this is NO2, and that's O2. We don't even have O3 in this one, but we do have O3 in this one. But guess what? It's on this side. We want it to cancel out the O3, so we got to flip this reaction. Now when you flip a reaction, you take the reactants, put them on the product side, take the products, and put them on the reactant side. So we flipped it. If you flip the reaction, you have to flip the delta H. So now we have positive 142.3. Okay. All right, so that'll take care of our O3 on opposite sides. But wait, now I notice that this reaction has, let's see, what do we got here? We want an O. And when we're done, we want just an O atom on the left side. But over here, it's on the right side. So we have to flip this reaction. Right, 2 O's gives us O2. So we flip that. So we have to flip this. So that becomes negative 495. Okay, so whatever you do to the reaction, you got to do to the delta H. All right, but still, this isn't going to give us what we want. Because when we're done, we only want 1 O on this side. Okay, and let's see. And we want no O2. So if I take this reaction and I multiply by 1/2, then I take this reaction and I multiply by 1/2. And that's going to give me O and 1/2 O2. So I'd be saying, wait a second, what's going on? So let's see what happens when I add this together now. This is gone, and this is gone. So I bring down my NO because it's on the left. I bring down my O3 because it's on the left. I bring down my 3/2 of oxygen because it's on the left. And I bring down my O atom because it's on the left. On the right side, I have an NO2. Are you guys seeing what's going to happen here? I have an O2, I have an O3, and I have a 1/2 O2. So let's see what happens. NO stays, O3, left side, right side, see you later. 2/3 oxygen over here, 3/2 oxygen. 1 plus 1/2 is 3/2 oxygen. Bye-bye oxygen. It was fun working with you. And now we have NO plus O gives us NO2, which is our desired reaction. So what we have to do now is add up all these delta H's after we make sure we take care of the flips and the whatever we multiply by. So we have a negative 198.9 kilojoules because we didn't do anything to that delta H. We flipped this one, so this is now positive 142.3. And this one we flipped and divided by 2, so that gives us negative 247.5 kilojoules. And so now if I add all this together, I get negative 303.2 kilojoules. All right, so this is the delta H for this reaction. Okay, hey, is there more to this? You betcha. All right, so what if instead of getting a series of reactions, you're given delta H of formation of each thing in the reaction? Hey, don't worry, we can still do it. Memorize this formula, write it down, we're going to use it a lot, okay? So here's NH3, here's a table. So where would I get this information from? A table. One thing to note. These are called heats of formation, HF, heat of formation. And these heats of formation, delta H of formation of elements in their standard form, or regular form, equals 0. Elements in standard equals 0. Okay, so here's what we do. We need to find the delta H of the reaction by taking the sum of the delta H of the products. So here are the products, right? We have 4 NOs, right? And here's for 1 NO, but since we have 4 in the equation, we have to do 4 times 90, okay? Plus, because we're summing it up, 6 times negative 286. So this is going to be the products. I did this over here because it's the products, right? Minus the reactants. So the reactants, I have 4 NH3s. So I have to do 4 times the heat of formation of ammonia. Right, negative 46. All right. Plus, I have to sum up 5 oxygen. I look on this table. I can't find oxygen. What the heck? Oxygen is an element. It's a gas. At standard temperature and pressure, it's a gas. So it's a 0 for its heat of formation. Okay. Make sure you remember that. All right. So now I have to subtract. So I add these together. And I subtract. So I'm going to have negative 1,356 minus negative 184 plus a positive, and I get negative 1,172. What is the answer for this? This is kilojoules per mole, but when I multiplied by that coefficient, that was per mole, so this is kilojoules. Rock on, delta H. All right, we're getting to the end. I know it's been long, but stick with me because exothermic is a favored natural occurrence. Why do we mean favored? We mean that anytime there could be an exothermic reaction, it seems like it naturally happens, okay? Why? Exothermic means lower energy. So look, you go low. Go low means stable. All right. So go low is more stable. Low energy is more stable. High energy is high stress. All right. So when you have to make the climb, that's activation energy. This is high energy. Go low is more stable. Okay. So kinetics is about the rate of reaction. Reactions occur in steps mostly. The slow step is the rate determining step. Intermediates are formed in one and then used up. Catalysts are there to start and there when you finish. Catalysts don't get used. They just give a different path. Collisions, bang up job. Woo! Energy diagram is always up and down. Break 'em, make 'em. Know your stuff. Break 'em, make 'em. Break 'em, make 'em. Okay. Finally, calculating delta H. If you get a set of reactions, add up the H's after you flip them or multiply or etc. Alright, make sure to flip the H's or multiply the H's. What if you're given heats of formation? Then the sum of the products minus the sum of the reactants. Right? I know this was long, but hey, you can't beat it when you got the climb. Alright, it's always going to be an uphill battle, kids. Alright, just do it because chemistry is the best. Peace out.